In example number 5, we're going to see a non-trivial example of where we have to calculate the limit of a sequence using the monotonic sequence theorem. Now, take a look here at what this actually says. We want to show that this sequence, which is actually a sequence we saw back in example 2 in this section. We want to show that this converges and then find its limit. Well, notice then that this problem is being broken apart in kind of to two different pieces. Convince me that the sequence converges, find its limit. So let's start with the first part. Does the sequence converge? Well, let's recap what we know from example 2. From example number 2, we know that a sub n is eventually strictly decreasing. Okay, so this is really good because I can go ahead and think about that if I already know that it's eventually strictly decreasing, I could plan to use the monotonic sequence theorem to say that if I can find that it's bounded below, I would know it converges immediately. That's fantastic. Okay, so let's see. Is this sequence going to be bounded below? Well, can I ever get negative numbers out of this sequence? It doesn't seem like it, so I could probably say that a sub n is greater than or equal to 0 for all n, and so a sub n is bounded below by 0. So, by the monotonic sequence theorem, a sub n must converge. Of course, what that really means is that when I do the limit of a sub n, I know there has to exist some answer. Let's call it L. Now, some of you might be thinking, why did we even bother to use the monotonic sequence theorem here? Couldn't we have just actually said, hey, I'm working with this particular a sub n, and I want its limit, so let's just compute the limit. But notice that computing this limit is very difficult because it involves these factorials, and like, how do you answer the question for a limit like that? I don't know. We don't just want to guess, we want to be certain. So by taking this in kind of this two-step approach, what we've seen is that first, we found that the sequence converges. And now that we know it converges, we know it has a limit. Let's see if we can try to find what that value of L is. So here's what I'm going to go ahead and do. I'm going to go ahead and note the following. Let's note that a sub n plus 1 is actually going to be equal to 10 to the n plus 1 over n plus 1 factorial. Right? That's what happens if I replace all my n's with n plus 1's. Now, of course, there's no surprise that that's the same thing as writing 10 over in n plus a 1, that's 10 to the first, and then multiplying that by 10 to the n over n factorial. You can think about the definition of factorials to see that the bottom is actually the same as n plus 1 factorial. And definitely in the numerator, if I multiply those back together, I have 10 to the n plus 1. But the interesting thing here is that this is really 10 divided by, n plus 1 being multiplied by a sub n. So there's ultimately a connection here between the a n plus 1 and a n itself. Okay, well, this is kind of strange, but note that I could also then make the following observation. I'm going to go ahead and take the limit as n goes to infinity of both sides here, that is, of both of these green portions, and use the fact that, well, the limit as n approaches infinity of a sub n plus 1, that is, the limit of this right here, shouldn't that be exactly the same as the limit of this? Because like it's the same structure. If n's going off to infinity, then this power is getting really big really fast, and the n factorial is getting really big really fast, and this is just kind of like one step ahead every time. So these pieces here are actually going to have the exact same limit. And I already know that that is the limit L. I don't know quite what that number is, but I know it exists. So let's see what happens when we do this. I'm going to obtain that the limit of a sub n plus 1 as n approaches infinity should be equal to the limit as n approaches infinity of 10 for n plus 1 times a sub n. Okay, now I can simplify this a little bit. What I can do is on the left side, I know that's already equal to L. And on the other side, I can kind of separate this out into two different limits. I can do limit of the first piece, since I know that limit's existing, and the limit of the second piece, again, because I know that limit exists. If you go back to the limit laws from the previous section, remember that you can only make a move like what we did here if both individual limits exist. So now, I know I can go ahead and rewrite this as L equals, this limit is going to be 0, that limit is going to be L. 0 times L, of course, is just going to get me to, well, 0. But this means that L, the limit that I have, is actually 0. So, as a conclusion, I have that the limit of a sub n, as n approaches infinity, is indeed 0. Now that's a really awesome kind of two-step argument there, and this approach down here on this kind of second half is rather complicated. However, it's a strategy that we will actually use much, much later in the semester to show something that's very, very interesting. What we'll see is that we will use this again later in the semester to show something very similar, that x to the n over n factorial is going to have the exact same limit of 0. Notice x is kind of just a placeholder where this 10 value used to be. That is, I could essentially make the same argument regardless of whether I had a 10 in there or a 15 or a 2 or a 6.9 or a pi. It doesn't matter. So I'll write here that we will use this argument again in chapter 6, ultimately to show this fact here. And this is so important. I'm going to actually ask you to quickly go ahead and I'd like you to sign your page. Maybe date it, whatever the date in the calendar is today, right? So just get some date written down. And I'd like you to actually go ahead, record this, and then once you have that recorded down, I'd like you to go ahead and, I don't know, maybe contact a notary, get this officially notarized, because when the time comes for us to actually come back and look at this important fact in Chapter 6, I'm going to ask you to pull back out this example and to actually see that we did talk about how we could actually develop an argument here using monotonic sequence theorem to determine the limit of a sequence, the limit of a sequence with this particular formula. So again, the ideas here in 5.1.2 are a little bit simple, some of them. Some others are a little bit complex, and all of them just require a little bit of practice to get used to and to really feel like you can master them. So go ahead, take a look at those worksheets, make sure that you're feeling comfortable with the questions that are on there, and of course, if you have any questions, let me know.